Oops. Forgot one more thing. Hello. Good afternoon, everyone. Yeah, let's start. Okay, first, don't forget the due of homework 2 is today, I believe. So make sure to submit your homework assignments through Canvas by midnight. Otherwise, there might be some late penalty. That won't be good. And yeah, we want to emphasize again, you can print out the PDF and use your pencil or whatever pens on that and write an answer and scan it, upload to Canvas. Or you can, for example, if you have iPad, you write everything on the PDF file and save them, upload them. I mean, whichever is fine. Right? Just make sure that your writing is clear so that the TAs won't get confused. Otherwise, they probably deduct your points and you have to argue with them and there's some kind of back forth. That's not very convenient. And we have required the TAs to give you the reason why, for example, if you like problem 2B or 3C, they get some point deduction. We require the TA provide the reason in the comments. So if you don't feel like, if you feel confused or not clear why you have some points deducted, look at the points, look at the comments, and you can also reply to the comments. If you want to argue with the TAs, please make sure that to do that like within 1 week. The homework grading has been released, and make sure the TA has replied to you in time. Like if the TA doesn't reply to you, and just let me know. I will just push the TA to reconsider according to your feedback. Okay. And again, our new quiz will be released after this class, and please make sure take some time to finish quiz, 20 minutes, 2 choice problems. That should be sufficient, but don't just open the quiz and doesn't do anything. You're gonna consume the time limit, and there won't be ways for you to retake the quiz. Okay, any question? Great. So in the last lecture, we introduced the continuous random variables, right? So you see that actually the discrete random variables are just a few, but there are like tons of continuous random variables. So it is very important to understand the definition and the insight about the continuous random variables. Here we just want to give a review to make sure everyone on the same is on the same page and is feels comfortable before we talk about several commonly used distributions for continuous random variables. Okay. So random variable, as we previously have defined, right, is a mapping, right? It's a function which maps from the sample space to a real world space. So the sample space it just contains is a space that contains all possible outcomes of your random experiments or whatever random phenomenon you are interested in, right? It could be like a temperature, it could be the gambling results, it could be like an investment, it could be profit, it could be economic index, it could be whatever you are interested in, as long as you believe it has some like randomness in nature. And then we propose or we define this so-called random variable that maps every outcome in the random phenomenon you're interested in to a real number, such that you can just look into the mapped numbers in the real world space. The benefit is that, okay, because everything, anything of random, they are mapped into the same space, which is just number space, right? It is abstract, but it is unified, right? You don't need to really care about what does this outcome really mean, right? What I care about is that okay, those are numbers, right? These numbers, those mapped numbers, namely the value of the random functions, how do they vary, and the change of those values, how will the change of those values will influence the probability and so on, right? So we can study some kind of common rules or laws from this mapped space. That's the major motivation of the random variable. Okay. So we have spent a few lectures talking about discrete random variables, which basically means that the omega, the sample space, are discrete and finite. For example, you flip a coin, you only see head or tail, right? So your sample space will only contains two elements, either head or tail, right? If you do binomial experiments, meaning that you try flipping the coin multiple times, you will see a sequence of the heads or tails, right? All possible sequences of the head and tails constitute our sample space, right? So like, suppose you do 3 times independent Bernoulli experiments, right? The sample space could be all the sequence of 3 results, right? You just enumerate, right? Something like that, right? But again, this sample space still include only a finite number of outcomes, right? And if we consider a more complex scenario where the sample space is infinite and uncountable, for example, let us assume omega itself also is a real space. Right? This is not rare. Actually, if we consider looking to the temperature, right? The temperature itself is a continuous number, right? It's a real number, right? So your sample space, meaning the rate from your device, which measures temperature, is a continuous rate, right? It's a real number, right? It's not like 31, 32. It could be 31.113, something like that, right? As long as your rate is accurate enough, right? So if your random variable definition, your original sample space also happens to be continuous, we call this random variable as a continuous random variable, right? So you see the difference, right? The difference from the discrete random variable, right? Discrete random variable just means, okay, the image of this mapping, which is omega, right, is discrete, is finite, right? And for continuous random variable, the sample space omega is continuous and infinite, uncountable. Continuous basically means it must be infinite and uncountable. Okay. So what's the big difference, right? What's the essential difference between continuous random variables and the discrete random variable, right? We spent a while discussing about that, if we can recall, right? The biggest difference is that suppose I have a random variable t, right? We mentioned that, okay, I can define an event, right? Like t equals to some number. This is event, right? This event actually means the set that contains every outcome in the sample space at which the random variable evaluated at this outcome is 5, right? So it's basically just a subset of the image. Like remember, this is just recall our jargons, right? The function, the original space, which map to the target space, right? The original space is called image, and the target space is called range, right? So, and we can define an event as the random variable value takes a particular value. This defines the event that includes all the elements in the sample space such that evaluating at this element, the value of the random variable is 5, right? So in a discrete random variable, we can always compute the probability of this event, right? It's typically not 0, right? Typically some number. Does it make sense? However, if t becomes a continuous random variable, what's the probability for this event? Can anyone recall? Yeah, it becomes 0, right? Why it becomes 0? Because your sample space now becomes infinitely large, right? There contains too many elements, right? So if you want to recall how we arrive at this conclusion, we can quickly look at this example again, right? So here we introduce a random variable t. We record the time elapsed from the starting of the class until the last person arrives. So we know t can take the values from 0 to 80 minutes, right? Because our class is just 80 minutes. So you start from the class, maybe the last person arrives from 0 minutes from the start of the class. That's very good, right? Usually it's not possible, right? But after 80 minutes, the class has already ended, right? So that means the last person arrived at class won't be longer than 80 minutes. Okay? So it gives a range of t. Okay? So if we consider the measurement of the t, right? The t is the time, right? And you consider different, consider using different watches to look at time, right? And like we can start with like very rough watch, meaning that it can only count per minute. It can only count per minute. Then the sample space will be what's the sample space? What's the sample space for t? Yeah, 0, 1, 2, 3, 4, 5, right? So until the minute 80 minutes, right? So in this way, like consider your watch, the stopwatch can only read every minute, right? Per minute. Your sample space is still discrete finite, right? So it contains 0, 1, 2, 3 until 80, right? So now I want to ask you, in this sample space, what's the probability of the event t equals to 5? Yes, one actually someone pointed out is 1 over 81, right? Because we got 81 elements, including 0. Yeah, right? So it's 181. This is a finite. In this case, like t is a finite random variable, right? It maps time to time, right? So identity mapping is from the omega to R, right? So basically T omega equals to omega. Omega is just the time, right? Omega belongs to this big omega, right? So now if we, oh, by the way, any question so far at this point? Everyone's comfortable? Okay, so now let us assume like we kind of buy a new watch, right? Which can count every 30 seconds, right? And then our sample space becomes larger, right? Because I count not only every minute, but every 30 seconds. So my sample space will be like 0, half minutes, 1 minute, 1 hour, sorry, 1.5, 2 minutes, 2.5, 3 minutes, until 79.5, 80 minutes, right? Does it make sense? Right? In this case, the omega is still discrete and finite, right? But what's the sample space? What's the number of the, what's the size of sample space? What? Yeah, I guess there's just the sample space should be 81 plus 80, right? Because between there are like 81 numbers and there will be 80 intervals, right? Each interval you gotta have 1 point in the middle, right? So it's 81 plus 80, which are in total 161 outcomes in the sample space, right? So now I want to ask, what's the probability in this new sample space? T equals to 5. What's that? Yes, 1 over 161, right? Here we're assuming like, okay, it's a equal chance to see any every outcome, right? We're not assuming like any weird and complex cases, right? Here we're assuming that, okay, you got an equal chance to say the time the last person arrives, right? So here our sample space now contains 161 elements. Then the probability your late arrival time is 5 minutes will be 1 over 161. Everyone agree with that? Anyone disagree? Right, we can keep doing this, right? Like assuming, okay, I got even better watch, which I can count every second. Not just minutes or half minutes, I can count every second. Then the sample space is still discrete and finite, right? But the only difference is that, okay, I'm gonna have a lot of more sample outcomes, right? So it could be 0 second, 1 second, 2 second, like 60 second, that corresponds to 1 minute, right? And 61 second, 62 second until, 60 times 80 seconds, which is 4,800 seconds, which is 80 minutes, right? So in this case, what's the size of the sample space? If I consider every second throughout 0 minute to 80 minutes, how many seconds do we have in the sample space? Yes, exactly, right? If we just include every seconds in this time range, will be 4801, right? Now, if I want to compute the probability that your t is still equals to 5 minutes, what's that? Remember, the 5 minutes is just the 300th second, right? It's still within this big sample space, has the equal chance with other seconds, right? So the probability is 1 over 4801. Does it make sense? Yeah, if we can use I mean, we can keep increasing the accuracy of our watch, right? And you can use atom watch, which their accuracy can be like 10 to minus 16 seconds and so on, right? So if you're using a more and more accurate watch, what will happen? What will happen? Yes, that means like you're gonna more and more time points added into this sample space, right? And meanwhile, your probability for the same event will get smaller and smaller. Why? Because your sample space grew larger and larger. It contains more and more outcomes, right? Now, let us push to the limit, meaning that I have a watch which is infinitely accurate, meaning that it can record any continuous time during this range. Then your sample space becomes infinite, right? It will contain infinite many elements. The size of your sample space will approach infinity, right? Then if we calculate the probability for this guy, it will be 1 over infinity. It's just 0. And we know at the infinity, our t becomes a continuous random variable. Does it make sense? Right here, we just give a intuitive explanation for this. But regarding why under the continuous random variables, your probability over an event defined as like t equals to something must be 0. This has a profound mathematical insight. Here, we just want to give you an intuition. Actually, if you allow this guy to be non-zero, then your probability system will be contradictory. There's a very famous paradox in this to illustrate you cannot do that. But here, we just want to give you intuition. Like when you generalize your sample space from finite discrete to more and more until infinite, you will naturally derive that the probability over this type of event, namely the random variable takes a particular value, will approach 0. But in fact, to maintain the mathematical consistency and to maintain like there won't be any contradictory conclusion in your probability system, you have to make this result. But that's out of our scope, right? It's not. This is not a theoretical course talking about probability theory and measurement merit theory. It's not that course. If you're interested, you can take a look at any merit theory-based probability block. It will explain to you in a much more rigorous but mathematically. Okay, and everyone you just need to keep in mind that's the big difference between the random variable, continuous random variable, and discrete random variable. For discrete random variable, well, you are free to compute the probability for us for this event, right? But for the same type of events, for continuous random variable, we have to assign the probability to be 0. Okay, any questions so far at this point? Great. So then we're going to introduce under continuous random variables 2 fundamental functions. One is called a probability density function. One is called a cumulative density function. So this probability density function is the counterpart of the probability mass function, right? I'm not going to write probability. This word is too lengthy, right? I just want to highlight the difference, right? Probability mass function, right? So in some literature, they're gonna like abuse these 2 notations. Like if you see some literature talking about probability density function, a discrete random variable, they are also, that just means they're talking about probability mass function. Okay, so what is probability mass function? It just defines the probability. See, this is a probability mass function. It just defines the probability that your x equals to some particular value. Right? As we mentioned in the discrete case, this guy has a reasonable meaning of the even definition. And it usually has non-zero probability, right? But for continuous random variable, as we mentioned, right? If you look at the probability of an even defined like this, it is usually 0, right? It is 0, right? So the probability density function is therefore defined in another way. It's kind of like indirectly. It's not that intuitive. So what's the definition of the probability density function for continuous random, right? So if we could represent the probability of the random variable in any range like a and b as an integration of a function f integrated from this range, and this function is non-negative for the whole range, and the integration of this whole function, the integration of this function in this whole domain, meaning negative, minus infinity, and positive infinity is 1, then we call this function f, this integration function f, as the probability density function. Is it clear to everyone? It's a little bit, it is a little bit lengthy, but doing such kind of definitions just to make sure it's mathematically rigorous. So basically, the probability density function is more like a mathematical term. It's not from like directly from like, okay, I want to look at what's the probability for a particular event. It's not like that, right? In other words, for a probability density function, right, fx, right, not fa, for a continuous run, for a continuous random variable, this guy is different from the probability that your random variable take the value a. This is different. Why? Because this guy usually is bigger than 0, but this guy in a continuous random variable case is always 0. Does it make sense? Right. So just make sure you're very clear about this difference, right? Okay. The probability density function is a tool to calculate a particular type of the events. Those events are represented as x random variables value belong to some range. Right? The PDF can be used to calculate the probability of this event through the integration, and the lower bound, the lower limit and the upper limit are the left and right ends of the range, and then your integration function is your density function. That's how this PDF is defined. Okay. Of course, we're gonna require additional properties, that is probability density function is always non-negative, and if you extend a and b to be minus infinity to positive infinity, then it should be, then this integration should be 1. This is reasonable because this just means the probability x belongs to minus infinity and positive infinity. This is event with probability 1, right? Because X, no matter how you mapped from the original sample space, is always between minus infinity to positive infinity, right? Because it's a real number. His real number is always inside this range, right? So this guy is 1. Okay, any question regarding the definition of the PDF? Everyone's comfortable? Okay. So next, based upon the PDF, probability density function, we define the so-called cumulative distributive distribution function, CDF. Okay. The CDF is defined as the probability for a particular type of event. So this type of event actually is the same as we have seen for the definition for discrete random variable. So the CDF function is defined as the probability that of the event that X less than or equal to some given A. So the CDF, its definition is the same as in the discrete case, right? If you can remember, right? But if we associate, if we connect to the definition of PDF, we just introduced, right? X less than or equal to A just means X is in the range minus infinity to A, right? So according to the definition of the PDF, the probability density function, the calculation of this probability is the integration of the PDF function, right? The lower limit will be a minus infinity, and upper limit will be A, and the integration function is the PDF function. Okay, so that's how we get here. Any question? Is everyone comfortable? Okay, I mean, this is just mathematical definition, and don't ask me why they propose this, right? This is kind of being like established for at least 150 years, right? So yeah. But from the definition here, we see the CDF essentially is an integration of the PDF, right? And what we can observe, or what we can conclude from this definition, from this relationship, using our knowledge from calculus 1. Any thought? So look, this is a function of A, right? CDF is a function of A. And this function is computed from an integral from minus infinity to A with the PDF, right? So now from this, what we can observe? Yeah, if we just connect back to what we have learned in, yeah. Yeah, of course, yeah. So FA is the area of the curve, right? If you draw your CDF curve look like this, right? And at NA, sorry, it's the PDF, right? The CDF value at A is actually the area covered by the PDF up to A, right? But from an analytical perspective, we know big F of A is just the integration function, right? Or antiderivative. In other words, if you take the partial derivative of A, F over A, what's that? It's your PDF small f evaluated at A, right? Right. This is I mean, this is a result from the calculus 1, right? If I have an integration function look like this, right? F A equals to something from minus infinity to A, and the integral is this small x, right? We have a partial f over partial A at A is your integral f, small f, lowercase f, evaluated at the upper limit A. Does it make sense? Right? So that means small f, the PDF, is the derivative of the CDF, right? On the other hand, this capital F, namely CDF, is the antiderivative of PDF, right? I mean, if you if you still feel uncomfortable, never mind. Just remember that it's very, very important relationship. Right? This is reflected from the definition. Okay. Any questions so far? So you will see that actually in when we talk about the continuous random variables, the most important things that are associated with this continuous random variables are these two functions: the PDF, the probability density function, and CDF, the cumulative density function, a cumulative distribution function. Okay. So all your properties about these random variables are reflected in these two functions. That's why their definition is really, really important. Okay, so then let us look at a few concrete cases, right? All those examples are almost the most widely used continuous random variables in real world. That means you really need to know those distribution and their PDF. You don't need to memorize the CDF because the CDF is just an integration of the PDF, right? But at least you should be aware their form of the PDF. Okay, the first one is called a uniform distribution. So what is uniform distribution? It's just that the extension of equal chance outcomes to continuous sample space. If we go back to our examples, this T random variable, right, which record the time elapsed since starting of the class of the last person arrival, right? We know its range is in between 0 and 80, right? If we assume that, okay, this late arrival time has equal chance to be any element inside this range. That means like, okay, I have seen like last person arrive at 3 minutes later has equal chance as you see some last person arrive at 10 minutes or 10, 50 minutes. Sorry, 10.5 minutes and so on, right? Then we call this T follows the uniform distribution. So what's the general definition for the uniform distribution, right? So first, we need to specify the range of the random variable. So in general, we assume X is in a range like alpha and beta. Like going back to our late arrival example, the alpha equals to 0 and beta equals to 80, right? And the probability density function for a uniform random variable is defined as the step function, meaning that when X is in the range of this alpha beta, the PDF value is just 1 over beta minus alpha. Right? So I would ask, what does beta minus alpha mean? You got a range, right? You got a range, you got an interval, right? In this axis, right? You got alpha and beta, right? So now, who can tell me what does beta minus alpha mean? Yes, but here I don't want to use size. I want to use length, right? Right, because you're talking about an interval, right? I want to know what's the length of the interval. It's like this pen, right? If you look at within this pen, how many numbers can you place? The answer is infinite, right? Infinitely many, uncountable, right? Numerous. But does the pen has a length? Yes. And it has a length, it has a finite length, right? This pen is not infinite long, right? It just I guess 2 inches or 3 inches also, right? So we use beta minus alpha to measure its length. And the probability density function, its value inside this interval is just 1 over the length of the interval. And if your X is outside this interval, then the PDF value is simply 0. Okay. So if we look at one example, this is the PDF function look like. What does the PDF function look like? Now here alpha is 0, right? The beta is 2. Right? Alpha is 0 and beta is 2. And oh, sorry, this is a y-axis has some issue. It should be 1 over 2. Right? And for all the x values outside of this range, you see the probability density function is simply 0. Does it make sense? Right? So, and then given this, maybe it's more convenient for me to draw here. So to draw a PDF for uniform distribution, and this uniform distribution is specified by alpha and beta. So the PDF of this uniform distribution will look like this. When X, here is X, right, falls outside of this range, right, the PDF is simply 0. And when it is inside this range, right, the PDF value is a constant. This constant is 1 over the length of this interval. Okay. So why this is a constant? I just want to express that you got equal chance to say any interval. Say, suppose suppose I want to look at your random variable taken at this range, at this small subinterval, and at another subinterval. As long as these two intervals are of the same length, then the probability should be the same. For example, this might be 0.5 and 1, and the other range might be 1.5 and 2. So if your x follows this uniform distribution, that basically means, okay, x, the probability x are within this range is the same as the probability within this range. This is called uniform distribution, meaning that, okay, it doesn't, the probability is nothing to do with any absolute position of the range it falls in. Right? It only relates to how large the range your random variable's value falls in. That's why it's called uniform, right? If this probability will change along the particular, at which position this particular interval locate, right? Then it's not uniform distribution. Okay. Any questions so far? Yeah, let's take a 5 minutes break, and we're gonna do some a little bit calculus practice to derive the CDF for uniform distribution. Yeah.
Okay, so this was my branch. Had a 1/3 chance of picking blue, 2/3 chance to pick red, and then my joint probabilities of picking blue and red is 1/6, 1/6, 1/2, 1/6. Where I've been seeing like a lot of discussion is on this one. I said the probability of B given A, right? And then I derived it to be 1/6.
I cannot comment on your number you give me, but the formula
That
you're
is
applying, that's
correct.
correct.
Okay,
Definitely
'cause
correct, yeah.
A given B would
Times
be
B, there's a base rule, right?
would be probably if A given B would be the joint probability that I pick blue and you pick blue, right?
Yeah, it's like, okay, I first pick blue for B, right? And the given I pick blue, what's the conditional probability you also pick blue?
I also pick blue,
Yeah,
which
yeah.
would be 1/6, correct? Because that was my tree. Is this tree is that an acceptable tree?
Yeah, yeah,
Okay,
yeah, definitely.
okay.
Yeah.
That was it. Thank you.
For one of the box location is number 2. Alright, number 3. When I calculated the probability given the disease, or probably you have the disease given the test is positive, it came out with this number, but that seems kind of small. But would you think that that's in like a general correct range? This would be the total probability of the test being positive, right? Just calculated using the formula of T given D times PD, even not D times P not D.
Yeah, the formula appears correct to me, but I don't know whether this number is calculated correctly. If you can make sure of this, I think that should be fine. Yeah.
And then the other one I had a question on was question D, which was the probability if you pick the, I guess if I pick a blue ball, probability you pick the ball.
Yeah. This idea is correct, but for the number I won't check for you. You should make sure it's correct.
Oh, wait, sorry, what?
I mean, the idea, the thought for me is correct. But I won't be able to check this for you.
And then, would I have to upload it as a PDF or could it turn into just like a name section?
Scan.
Oh,
You
okay.
can scan and upload through cameras. Yeah. Okay. Yeah, hello everyone. Let's continue. Yeah, we have just introduced the PDF for the uniform distribution, right? You see that it's nothing but you put a constant for your PDF value at the range and put 0 for any value outside range. And this constant is just 1 over the length of the range. That's the uniform distribution. That's the PDF definition for the uniform distribution. And this uniform distribution is often used to model events, although you have a continuous outcome, but you can roughly believe that, okay, your events will happen at any position for this range, right? That's just used to model this kind of phenomenon. Like, for example, like you threw a dart, right? You got target, right? And threw a dart. If we don't make any assumption, we're gonna assume, okay, the chance your dart hit at any point in this target is the same. We want to, if you want to believe your observation where your dart hit on the target look like this, then use uniform distribution. Of course, this might not be true because you also have some chance to to miss the whole target, right? That's another story, right? And to account for that, you probably want to seek for other distribution. Here we just give one example, right? The other example might be, I don't know, like let's say if I threw a ball on this table, right? And I'm assuming, okay, I never miss, right? I'll always throw a ball on this table. But according to at which position, which point the ball hit on the table, I don't know. And then I assume, okay, my ball has the equal chance to hit every possible surface point at this table. Then I'm going to use uniform distribution. Okay. So now let us look at how do we calculate the cumulative distribution function. So this one is like more like a calculus practice, right? Because we're going to leverage the definition. So we know that the CDF essentially is just an integration or antiderivative of the PDF, meaning that if we want to evaluate the CDF at any point A, you're going to do an integration from -infinity to A with the PDF function, right? That's our definition. Okay, if we take a look at here, is here, right? So now we just apply this, right? So we see this f of x is kind of like a step piecewise function, right? So when we do this integration, we need to consider how do we pick up a, right? How do we choose a? Like this is a f, right? I mean, this is fx, right? Now I'm gonna integrate f from minus infinity to a given point a. Now, which cases should we consider? Any thought? It start with alpha, right? So you have to consider whether your a is here, see, less than alpha, or u is in the middle, between alpha beta, or bigger than beta, right? Those are three cases we should consider. Because on the three cases, you actually, the value of your density function is different, right? If your a is less than alpha, according to our definition, which we know that the probability density function will be 0, right? But when your a is between alpha and beta, your probability density function is a constant, a non-zero constant, right? However, when your a is bigger than beta, the density function becomes 0 again. That's something we should take care during our calculation. Right? Does it make sense? Right? So let's just do this, right? So consider the first case where we have alpha less than a. Sorry. A less than alpha. It's here, right? So our integration becomes what? In this case, what's the value of the probability density function, small f? Yeah, this is the small f, right? When a less than alpha, what's the value of the PDF? It's just 0, right? That's the definition. It's 0. So that means like you're gonna integrate with 0 function. Of course, the integration result will be 0, right? Okay. So in the second case, a is in between, right? In between alpha and beta. So alpha less than equals to a less than equal to beta, right? And then how do we compute the integration? In this case, we know that the PDF, the lowercase f, right, will always be 0 until it reaches alpha, right? So that means the integration up to alpha is always 0. Okay. This part is always 0. And only from alpha to a here, you have a non-zero constant function, right? So this guy will be alpha to a, and this constant value is 1 over beta minus alpha, right? So this, what's the value of this guy? let's just push ourselves to yeah, calculus 1, right? Yeah, this 1 over beta minus alpha should be moved out of the integral. Why? Because it's constant to the integration variable x, right? Then what's the result? Anyone can rate it for me? No, you see here we just break the whole integration into 2 parts, right? The first part is from negative to alpha, but we know that at this case, the integration function is 0, right? Yeah, so this guy must be 0, right? Yeah, how about this guy? Yes. Yes. So what's that? Well, it's just a minus alpha divided by beta minus alpha. Okay. I mean, if you feel uncomfortable, that's easy. Just open your calculus box and find out how this is calculated, right? This is just the integration of a constant function, which is just the upper limit minus the lower limit. Right? So it's a and b dx. What's that? It's b minus a. Right? I mean, again, if you feel like this is kind of a little bit unfamiliar, uncomfortable, or blurred, never mind. Just take a look. Or even you can search on the web. It's just some knowing results. There's no need to struggle on that. Okay. So then we see that in the second case, where a is between, alpha and beta, I should use another color. CDF function is a minus alpha divided by beta minus alpha, right? Okay, the third case. The one thing I would like to mention that this guy actually is just a line, right? So remember that the input is a, right? It's a linear function of a, right? It has a coefficient which is 1 minus beta, 1 over beta minus alpha, right? So then in the third case is a is bigger than beta, meaning that a is here. Now what's the CDF value? Is what? A is bigger than beta. So a is here. Why is 0? Yeah, of course. The PDF is 0 for sure, right? But here we're talking about CDF. Why is 1? Yes, your intuition is right. What we need is just to verify this from our calculation, right? So again, we just follow the definition, right? It's just minus infinity to a and fx dx, right? You have to integrate f up to a. Right, this guy, as we mentioned, we can break it into 3 equations. First, from minus infinity to alpha, meaning here. We know that in this range, f, lowercase f is always 0, right? And the second range is inside alpha and beta, right? So it's from alpha, beta, and in this case, in this range, the f value is this constant, right? Which is 1 over beta minus alpha dx. Right? And in the third range is from beta to a. Okay. So the third integration is from beta to A. And in this range, we know the PDF, the lowercase f is 0 as well, right? Does this make sense? Okay, so let's do this. Okay, so we'd like to calculate the CDF, right? According to the definition, it is an integration from minus infinity to A, and the integration function is the PDF function. We agree with this, right? Then the question is, how do we choose A, right? And here is the curve of our PDF function f, right? When we choose A to be bigger than beta, meaning on the right-hand side of beta, that means our integration is gonna go through 3 areas, right? One area is from minus infinity to alpha, right? And second area is from alpha to beta. And third area is from beta to A, right? We can break this whole integration into the integration over 3 ranges, right? It's just the rule of doing the integration, right? If you feel uncomfortable, then never mind. It's just a rule. You just need to memorize. Like this is calculus 1 rule, right? So we can break this whole integration, meaning from minus infinity to A, into 3 integrations. The first integration is from minus infinity to alpha, and the second integration is from alpha to beta, and third integration is from beta to A. Do we agree? Everyone's comfortable, right? Why do we break them into 3 integrations? It is just because the PDF, the small f here, will take different values on these 3 ranges. We want to deal with them separately and then aggregate them results together by summation, right? So in the first range, namely minus infinity to alpha, what's the value of this lowercase f? What's the value of the PDF, small f? From negative infinity to alpha? 0, right? So here we know the integration function is 0 and times dx, right? Then this integration is simply 0. Does it make sense? Right? And then in the second range, which is here, right? When x belongs to alpha and beta, what's the value of our PDF? It's not 1, it's 1 over beta minus alpha, right? So that means in the second range, you're gonna calculate this integration from alpha beta, and the small f x is beta minus alpha and times dx. What's that? Yeah, that's 1, right? If you just calculate this 1. Does it make sense? Right? So this is just 1. And for the third integration, that is from beta to A, right? What's the value of our lowercase f? Still 0, right? So in the third integration, you're gonna still integrate with 0 in this range, which is also 0, right? Does it make sense? Now, if we add them together, 0 plus 1 plus 0, it is 1. Any question? Like if you doubt about the computation, the calculation procedure, or if you're like uncomfortable with that, and it's just you know, that means you haven't practiced the calculus 1 for a while. That's the only reason. There's no other reason. I will we'll recommend you to look at how we do the, just the ordinary one-dimensional function integration. You will definitely feel much more comfortable. But here we just want to emphasize the whole computation procedure. Like how do we derive the CDF out of PDF function? So basically you're gonna do some integration. That's it. Okay. Yeah, if we take a look at the what does CDF look like? It will look like this. Right? If we just write down the CDF function, right? FA when A is less than alpha is 0. When A is between alpha and beta, it will be A minus alpha, beta minus alpha. Sorry. When A is bigger than beta, it becomes 1. Right? You see, this is alpha, right? This is a beta, right? So less than alpha is 0. And between alpha and beta, it is here, A minus alpha, beta minus alpha, right? And according to A, it's just a linear function of A, right? It's A is 1 over beta minus alpha times A subtracted by alpha over beta minus alpha, right? It's just a linear function with some coefficient, with some tangent slope and the intercept, right? That's why you see a nice red line like this, right? And then after A is bigger than beta, it becomes constant 1 again. So this is a CDF form for uniform distribution. Every time you look at this guy, you should kind of like immediately react that this is a uniform distribution. Any questions so far? Okay. The second distribution we would like to introduce is called the exponential distribution. So the requirement for this exponential distribution random variable is that x must be non-negative. So the PDF is defined in this way. So lambda times e to the minus lambda x. And here lambda is a parameter of this distribution, which is always positive. And then we can denote a random variable under exponential distribution in this way. X follows some exponential distribution with parameter lambda. So what does it mean, right? What does this distribution, what is this distribution used for? It is often used to model the waiting time. For example, you buy something, right? You buy a coffee, right? In Starbucks, right? You're always in your queue, right? You want to look at, of course, the time you wait until you get a coffee is a random variable, right? You don't know like whether you're gonna immediately get your coffee or you have to wait for 15 minutes, right? So, or you can view like you're waiting, you're ordering some like a to-go menu, right? And you still need some wait because in front of you there could be other customers or users, right? So then we're interested in what's the uncertainty about your waiting time to get your service. So this waiting time is often modeled as an exponential distribution variable. And it is also used to model the interarrival time. Like if you look at some events to happen, right? If those events follow some like a Poisson distribution, for example, the if you sit in front of some crossroad, right, you want to count how many cars are passing by every day. Right? Today might be 20, tomorrow might be 30, Thursday might be 25, and Wednesday might be 5, right? So this count, namely how many vehicles passed over that crossroad, is usually modeled as a Poisson distribution. Then the interesting thing is that if that really follows Poisson distribution, then the inter-arrival time between two vehicles, say, you see one BMW passing to that route, and then after 5 minutes, you see a Jeep. This inter-arrival time will follow this exponential distribution. Okay. This is like too frequent usage of this exponential distribution around the variables, waiting time or inter-arrival time between some type of events. Okay, so let's stop here today. We're going to continue just introducing those commonly used continuous random variable distribution on Thursday.